A beam of light leaving Earth today will still be traveling long after every city now standing has changed beyond recognition. After languages have shifted, after borders have vanished, and after thousands of years of human history have quietly passed, just to reach the nearest star beyond our own. That is the problem hidden inside the night sky. The universe looks open, luminous, and close enough to touch, yet distance keeps it sealed. Even the fastest thing that exists cannot make the crossing quickly. What feels like motion becomes waiting, and waiting stretches into eons. Crossing our galaxy takes light roughly 100,000 years. These are not travel times in any human sense. They are geological. They are historical. They exceed the lifespan of civilizations. Human technology barely enters the equation. The fastest spacecraft ever built would need tens of thousands of years to reach the nearest star. A mission launched today would arrive in a future that no longer remembers why it was sent. For most of modern science, this was not a challenge to be solved, but a condition to be accepted. Faster-than-light travel belonged to imagination, not physics. The universe had a speed limit, and nothing with mass could cross it. But that conclusion rested on a quiet assumption. It assumed that travel must mean moving through space. That assumption is now being questioned, because while physics forbids objects from outrunning light, it places no such limit on space itself. On the largest scales, the universe already stretches faster than light, carrying distant regions apart without breaking any physical law. Once that detail is noticed, the problem changes shape. The question is no longer how to go faster, but whether distance itself can be altered. Not by breaking physics, but by using it more completely than ever before. That is where the idea begins. Not with engines or fuel, but with the structure of space-time itself. For centuries, people assumed distance was simply a matter of effort. If something was far away, it meant the journey would be hard, not impossible. Build better ships, stronger engines, smarter routes, and eventually the gap would shrink. That belief worked on Earth. It worked across oceans. It even worked when humanity first left the planet. Space broke that logic. As understanding deepened, it became clear that the universe was not merely large, it was structured in a way that actively resisted rapid crossing. Distance was not just empty separation. It was governed by rules that did not bend with ambition. A percenter of those rules sips a single number, the speed at which light travels. It is not just fast, it is absolute. No matter how quickly you move, light always pulls away at the same rate. This behavior makes no intuitive sense, yet every experiment confirms it. Reality rearranges itself to preserve that constant. To make this work, space and time cannot remain fixed. They adjust instead. Time stretches. Lengths contract. Events that seem simultaneous from one perspective drift apart in another. Motion reshapes reality to protect that speed limit. As an object accelerates, its energy rises. That energy behaves like additional inertia, making further acceleration increasingly difficult. Near the speed of light, the resistance becomes overwhelming. The equations do not soften. They do not negotiate. The energy required to reach the limit climbs without bound. This is why faster-than-light travel was dismissed so confidently for so long. It was not a matter of insufficient technology or inefficient design. It was the universe enforcing consistency. Particle accelerators confirm this daily. Subatomic particles can be pushed astonishingly close to light speed, but each fraction gained demands disproportionate energy. The closer they get, the harder space-time pushes back. Long before the limit is reached, other consequences appear. Time itself begins to separate travelers from those they leave behind. A journey undertaken at extreme speed would not just carry someone across space, but across eras. While the traveler experiences a compressed passage of time, the outside world ages rapidly by comparison. Distance becomes separation in history. Acceleration adds another constraint. Reaching such speeds quickly would require sustained forces that biological bodies cannot tolerate. Stretching the acceleration over longer periods reduces the stress, but reintroduces the original problem. The journey becomes long again. Speed and survival pull in opposite directions. By the late 20th century, the conclusion seemed unavoidable. The universe allows observation across immense distances, but it does not allow access. Telescopes could peer into atmospheres of distant planets. Spectroscopy could reveal chemistry light years away. But physical travel remained trapped within a small neighborhood around a single star. The stars were visible, measurable, and forever out of reach. And yet, hidden inside the same theory that closed that door was a detail most people never noticed. Relativity forbids objects from moving through space faster than light. It does not forbid space itself from changing. On the largest scales, the universe already demonstrates this distinction. Space expands. Distant regions recede from one another faster than light, not because anything locally breaks the limit, but because the space between them stretches. No law is violated. The rules remain intact. Once that behavior is acknowledged, the problem begins to loosen. If space itself can move, then motion might not require acceleration in the way it always has. Travel might not mean crossing distance, but reshaping it. The question shifts away from engines and toward geometry, away from speed and toward structure. That shift was small on paper, but enormous in implication. It suggested that the barrier humanity had accepted for generations might not be a wall at all, but a misunderstanding of what motion really means. And that realization set the stage for one of the strangest ideas modern physics has ever taken seriously. Up to this point, every attempt to imagine interstellar travel followed the same instinct. Go faster, build stronger engines, push harder against the void. The universe answered each attempt the same way, not with resistance you could overpower, but with limits that grew sharper the closer you approached them. Every propulsion system ever conceived shares a common ancestry. Something is expelled backward so something else can move forward. Fire, plasma, charged particles, even hypothetical nuclear exhaust. The mechanism changes, the principle does not. Momentum must be conserved. Energy must be paid. At everyday speeds, this cost feels manageable. Add fuel, gain velocity. But as speed increases, the relationship stops behaving kindly. Fuel has mass. Energy itself contributes to inertia. Each improvement adds weight that must also be accelerated. The faster you try to go, the more brutally the balance tips against you. This is captured by the rocket equation, a rule so unforgiving that even modest gains near relativistic speeds demand absurd increases in fuel. By the time a spacecraft approaches a meaningful fraction of light speed, the numbers explode beyond practicality. Not because engineers lack creativity, but because the mathematics refuses compromise. Even if that barrier could be ignored, the human body could not. To accelerate rapidly enough to make such journeys short would expose passengers to sustained forces that organs and bones cannot withstand. Stretch the acceleration to preserve life, and the travel time stretches with it. The universe offers no path where speed, biology, and energy align comfortably. For a long time, this was treated as the final word. Not a failure of imagination, but a structural verdict. The cosmos allows motion, but only at a pace that keeps stars isolated from one another. Humanity could explore locally, but never migrate meaningfully between suns. That conclusion rested on a single, deeply ingrained picture. Motion meant moving through space, like a ship crossing an ocean or a probe coasting through vacuum. Space itself was treated as passive, a background that could be crossed but never altered. General relativity quietly contradicts that picture. According to Einstein's equations, space and time are not static. They respond to energy and mass. Planets bend space-time. Stars curve it. Black holes deform it so completely that paths once straight become inescapable spirals. Gravity is not something acting within space. It is space itself changing shape. This matters because geometry governs motion. Objects follow the contours space-time lays out for them. They are not pushed along invisible tracks. They fall through curved structure. Change the structure, and motion changes with it. The universe demonstrates this flexibility constantly. Time runs slower near massive objects. Distances differ depending on motion and gravity. Even the size of the universe itself changes as space expands. On the largest scales, this expansion produces something that seems to violate everything learned about speed. Distant galaxies recede from one another faster than light, not because they are racing outward, but because the space between them grows. No object locally outruns light. The rules remain intact. This distinction had been understood for decades, but its implication for travel was rarely pursued seriously. Expansion was treated as a cosmological curiosity, not a technological hint. Space moved, but only because the universe demanded it, not because anything could command it. Then a different kind of question emerged. If space can expand and contract naturally, could it ever be shaped deliberately? Not pushed against, not traversed, but arranged. Could motion be achieved without acceleration by letting space-time itself carry a region along? This question did not arise from science fiction. It came directly from the equations of general relativity. The same mathematics that enforces the light speed limit also describes how space-time bends and flows. There was no separate rule forbidding extreme geometries, only a question of whether they could exist at all. At first, this line of thinking lived comfortably in abstraction. It was elegant, strange, and impractical. But physics has a habit of turning abstract questions into concrete surprises. In the mid-1990s, one physicist decided to see what the equations actually allowed, not philosophically, but explicitly. He asked whether space-time could be arranged so that a region moved faster than light relative to distant observers, while remaining locally calm inside. The answer was unexpected. The mathematics did not say no. In 1994, a physicist named Miguel Alcubierre explored that question in detail. He was not attempting to design a spacecraft or propose a practical engine. He was doing something more fundamental. He was asking what kinds of space-time geometries Einstein's equations actually permit. General relativity does not describe forces in the traditional sense. It describes how space-time curves in response to energy and mass. Once those equations are written down, the universe does not care whether a solution feels intuitive or absurd. If the mathematics is consistent, the solution exists. Alcubierre discovered one such solution. In this configuration, space-time behaves in a way that feels almost impossible at first glance. Space contracts in front of a region and expands behind it. The region itself remains locally flat and undisturbed. Nothing inside accelerates. No object within the region moves faster than light relative to its immediate surroundings. Yet the region as a whole can move arbitrarily fast relative to distant observers. This was not a metaphor or a thought experiment. It was a valid solution to Einstein's field equations. The key insight was subtle but decisive. Relativity forbids objects from moving through space faster than light. It does not forbid spacetime itself from being rearranged in extreme ways. Inside this structure, often described as a bubble, physics behaves normally. Time flows at a familiar rate. Forces remain gentle. A spacecraft inside would feel as though it were at rest, even as the surrounding universe changes position relative to it. The usual penalties of high speed disappear. There is no crushing acceleration. There is no relativistic time dilation separating travelers from those they leave behind. The journey does not involve fighting inertia or piling up energy. Motion occurs because space-time itself is doing the work. The idea immediately stood apart from every propulsion concept that came before it. This was not a better rocket. It was not an engine at all. It was a redefinition of motion. On paper, the implications were staggering. Interstellar distances could be crossed on human timescales. The light speed barrier remained intact locally, yet the effective speed of travel could exceed it by any amount. The universe's most rigid rule appeared to contain a narrow exception written into its own structure. But the solution came with a cost that could not be ignored. The space-time geometry Alcubierre described required a fall of energy unlike anything normally encountered. In order to contract space in front of the bubble while expanding it behind, the equations demanded regions of negative energy density, energy that behaves opposite to ordinary matter. Instead of pulling space-time inward, it pushes outward. This requirement immediately triggered skepticism. All known forms of matter and energy have positive energy density. Mass attracts. Gravity pulls. Negative energy sounded less like a physical resource and more like a mathematical artifact. Alcubierre himself did not claim otherwise. He did not present his solution as a blueprint. He presented it as a proof of concept, a demonstration that faster-than-light motion was not strictly forbidden by the laws of physics. The universe allowed it mathematically, even if it seemed impossible practically. Early estimates made the problem look hopeless. Calculations suggested that creating such a space-time distortion would require negative energy comparable to the mass energy of entire planets. Not stored, not converted, but arranged in precise configurations. The scale was beyond absurd. And yet, something fundamental had changed. The energy requirement, while enormous, was finite. That single detail mattered more than the numbers themselves. Physics treats infinity as a hard stop. Finite quantities, no matter how large, remain theoretically achievable. They represent ignorance and limitation, not impossibility. That distinction kept the idea alive. Over time, researchers revisited the original solution. Alcubierre's geometry was elegant but extreme. It assumed sharp boundaries and thick space-time gradients because those were mathematically convenient. When those assumptions were relaxed, the numbers shifted. Small changes in the shape of the bubble produced dramatic reductions in required energy. Smoother transitions, thinner walls, dynamic rather than static configurations. Each refinement reduced the cost by orders of magnitude. The energy demands fell from planetary scales toward asteroid scales, then lower still. They remained far beyond current technology, but they were no longer cosmically absurd. More importantly, these refinements revealed where the real difficulty lay. The challenge was not speed. It was precision. Warp motion did not require overpowering the universe. It required sculpting space-time with extraordinary care. For years, this remained purely theoretical. The equations allowed it. The models improved. But nothing in the real world hinted that such space-time geometries could ever be created, even briefly. Then physics at the smallest scales began to complicate that assumption. The requirement for negative energy initially looked like the end of the road. Ordinary matter could not supply it. Known fields did not behave that way. Gravity, in every familiar context, pulled inward rather than pushed outward. Warp geometry seemed to demand something the universe simply did not provide. But quantum physics has a way of unsettling conclusions that feel too comfortable. According to quantum theory, empty space is not empty. Even in a perfect vacuum, fields fluctuate constantly. Particles appear and disappear in pairs, borrowing energy for fleeting moments before returning it. This restless activity gives space a baseline energy level, one that cannot be removed, only rearranged. Under certain conditions, that rearrangement produces something remarkable. When two uncharged metal plates are placed extremely close together, separated by only a tiny gap, quantum fluctuations between them are restricted. Some wavelengths of virtual particles can exist outside the plates, but not between them. This imbalance creates a pressure difference that pushes the plates together, producing a measurable force. This phenomenon, known as the Casimir effect, has been confirmed repeatedly. Its importance lies not in the force itself, but in what it reveals. The space between the plates contains less energy than the surrounding vacuum. Relative to its environment, it behaves as a region of negative energy density. Negative energy, at least in this limited and controlled sense, is real. This did not solve the warp problem. The effect is extremely small and operates over distances measured in nanometers. Scaling it up to anything resembling a spacecraft would require precision and stability far beyond current capabilities. But it overturned a critical assumption. Negative energy was not forbidden. It existed naturally as a consequence of quantum fields. Once that door opened, the conversation shifted again. If negative energy can exist locally and briefly, then warp geometries were no longer demanding a fictional ingredient. They were demanding an extreme version of something already present in the fabric of space itself. The question was no longer whether such energy could exist at all, but whether it could be amplified, shaped, and sustained. At the same time, refinements to warp models continued. Researchers explored configurations that reduced reliance on large regions of negative energy. Some models redistributed the energy requirements. Others used oscillating or dynamic fields rather than static bubbles. Each approach revealed that the original Alcubierre solution was not unique. It was one point in a broader landscape of possible spacetime geometries. As these models evolved, attention began to shift from propulsion to verification. Instead of asking whether a spacecraft could be moved, physicists began asking whether the predicted spacetime distortions could be produced even at microscopic scales. The goal was not travel, but confirmation. If the geometry itself could be observed, then warp physics belonged to reality rather than speculation. In the early 2000s, experiments associated with space research agencies explored this idea using sensitive instruments and carefully arranged electromagnetic systems. The expected effects were extraordinarily small, far below anything that could produce motion. What researchers looked for was structure, not speed. Some measurements hinted at spacetime behavior consistent with theoretical warp-like configurations. Not propulsion, not movement, but distortions that matched the predicted shapes. The results were subtle and remained debated, but they were not random. They aligned with specific models rather than noise. This mattered because physics does not require usefulness to acknowledge existence. If a phenomenon can occur at any scale, it belongs to the universe's allowed behaviors. Scaling then becomes an engineering challenge rather than a conceptual one. Still, the energy problem remained dominant. Creating a warp-like distortion, even briefly, is difficult. Maintaining one stably is far more so. Warp geometries involve extreme gradients in spacetime. Any imbalance could cause asymmetric collapse, releasing intense radiation or trapping systems in distorted regions of space. Unlike conventional engines, warp systems do not fail gently. They interact with the structure of spacetime itself. Errors would propagate outward rather than remaining localized. As researchers confronted this challenge, an even stranger possibility entered the discussion. The universe is not just filled with matter and radiation. Most of its energy exists in a form that does not clump, shine, or behave like anything familiar. Dark energy drives the accelerating expansion of the universe. It exerts negative pressure, pushing space apart rather than pulling it together. This behavior is uncomfortably similar to what warp geometries require. Some physicists began to wonder whether the negative energy demanded by warp fields and the negative pressure associated with dark energy might be related. Not necessarily the same phenomenon, but perhaps different expressions of a deeper property of space-time itself. This idea remains speculative. Dark energy is poorly understood. We do not know how it behaves at small scales or whether it can be influenced in any way. But its existence reframes the problem. The universe already contains an energy component that naturally drives space-time expansion. Warp technology might depend not on creating exotic energy, but on learning how to guide or modulate something already present everywhere. Whether that is possible remains unknown, but the implication is profound. It suggests that faster-than-light travel, if it ever occurs, would not be an act of brute force. It would be an act of understanding. Warp physics stopped looking like a quest for power and started looking like a quest for control. Control over geometry. Control over energy distribution. Control over the subtle relationship between quantum fields and spacetime itself. Progress in this area does not look dramatic. There are no launches, no engines roaring to life. It looks like improved sensors, refined simulations, and laboratories measuring effects most people would dismiss as background noise. Yet history suggests that this is how foundational technologies begin. Quietly, indirectly, with ideas that seem disconnected from everyday experience, until suddenly they are not. And if space-time can be shaped deliberately, even briefly, then it cannot be shaped invisibly. That realization leads to a final, unexpected question. If warp-like distortions exist at all, then they should leave traces behind. And if traces exist, the universe itself may already be carrying evidence that faster-than-light travel has occurred somewhere before. Space-time does not change quietly. Whenever massive objects move, accelerate, or rearrange the geometry around them, space-time responds by sending ripples outward. These ripples, known as gravitational waves, are not disturbances traveling through space. They are disturbances of space itself, stretching and compressing reality as they pass. For most of the 20th century, gravitational waves existed only on paper. Einstein predicted them, but even he doubted they would ever be observed. By the time such waves reached Earth, they would be unimaginably faint, diluted across vast distances. Then, in the early 21st century, they were detected. Two black holes collided more than 1 billion light-years away. The violence of that event reshaped space-time so dramatically that its echo was still measurable when it reached Earth. Instruments detected distortions smaller than the width of a proton, confirming that space-time carries information across the universe. That discovery changed how physicists think about motion and visibility. If natural cosmic events leave signatures in space-time, then engineered space-time distortions would do the same. A warp-like geometry is not a gentle adjustment. It involves sustained compression and expansion of space, arranged deliberately and maintained over time. According to general relativity, such behavior must produce gravitational radiation. Crucially, the pattern of that radiation would differ from anything produced by natural astrophysical processes. Black hole mergers create brief chirps, rising quickly in frequency before fading. Neutron-star collisions leave signatures shaped by nuclear matter and violent disruption. A warp bubble, by contrast, would generate a coherent, directional space-time disturbance. Not an explosion, but a moving structure. Not a momentary flash, but a sustained signal tied to geometry rather than mass collision. Theoretical models suggest that such a signature would be difficult to confuse with known sources, provided detectors are sensitive enough. The signal would encode information about the shape of the space-time distortion, its velocity, and the way energy is distributed around it. This possibility opened a remarkable shift in perspective. Instead of asking when humanity might build warp technology, some researchers began asking whether it might already exist somewhere else. Not nearby, not visibly, but encoded in the fabric of space-time itself, traveling outward long after the event that created it. Space-time does not erase disturbances. It carries them. Every gravitational wave ever produced continues to propagate outward, thinning but never disappearing. In this sense, the universe acts as an archive, recording violent events and subtle structures alike. Somewhere within that record could lie evidence of space-time manipulation that did not originate from natural cosmic disasters. This turns the search for advanced technology into a form of cosmic archaeology. We would not need to see spacecraft directly. We would not need intercepted signals or deliberate communication. We would only need to identify a space-time signature that cannot be explained by known astrophysical processes. If such a signal were ever confirmed, its implications would be immediate and profound. It would demonstrate that faster-than-light travel is physically achievable, and it would confirm that technological civilizations exist, or have existed, beyond Earth. More than that, it would provide guidance. Gravitational waves encode information about the systems that create them. From a warp-like signature, physicists could infer geometry, energy distribution, and motion. It would be a form of reverse engineering performed across cosmic distances, extracting design constraints from space-time itself. This approach follows a familiar pattern in science. Humanity understood stellar fusion long before building reactors. Planetary motion was mapped centuries before spacecraft were launched. Observation has always preceded construction. Still, caution remains essential. Gravitational wave astronomy is young. The instruments are sensitive, but not yet comprehensive. Many cosmic phenomena remain poorly understood, and misinterpreting a signal would be catastrophic for scientific credibility. Any claim of engineered space-time would require overwhelming evidence, independent verification, and years of scrutiny. Silence, too, carries meaning. If increasingly sensitive detectors find no evidence of warp-like signatures, it may suggest that such technology is extraordinarily rare, extremely difficult, or constrained by deeper physical principles, not yet understood. That absence would still guide research, narrowing the space of possibility. What makes this search uniquely powerful is that it relies entirely on established physics. Gravitational waves are real. Space-time distortions are real. The connection between geometry and radiation follows directly from general relativity. No new laws are required, only careful listening. As detectors improve and space-based observatories come online, the universe will speak more clearly. Whether it reveals engineered signatures or only natural ones, the answer will arrive quietly, embedded in data, waiting to be recognized. And if one day a signal appears that cannot be explained away, it will not announce itself as technology. It will appear as a discrepancy, a shape that does not belong, a pattern space-time should not produce on its own. At that moment, faster-than-light travel would stop being an unfinished idea and become a demonstrated possibility, not because humanity built it, but because the universe revealed that it can be done. If warp-like travel ever becomes possible, its consequences would unfold gradually rather than all at once. The technology itself would not arrive as a finished capability, but as a sequence of partial successes, each one forcing a reconsideration of what distance actually represents. The first impact would not be human voyages between stars. It would be control. Before anything could travel, space-time would have to be shaped reliably in small, deliberate ways. Experiments would focus on stability rather than speed. Researchers would study how space-time responds to sustained manipulation, how distortions interact with surrounding regions, and how energy distributions must be arranged to guide geometry instead of tearing Kebra. It apart. This phase alone could stretch across generations. Even tiny space-time distortions would have profound implications. Distances could be altered by fractions too small to notice directly, yet large enough to affect precision measurements. Time could flow at slightly different rates within controlled regions, not enough to enable travel, but enough to test the limits of relativity in laboratory conditions. Effects once associated only with massive gravitational fields might be reproduced artificially, offering insight into how space-time behaves when pushed beyond its familiar regimes. Navigation would be rewritten long before exploration. If space-time geometry can be adjusted intentionally, then concepts like straight lines and shortest paths lose their usual meaning. Routes would no longer be defined solely by distance, but by curvature. A longer path through flatter space-time might take less time than a shorter path through distorted regions. Travel would become a problem of mapping geometry rather than plotting trajectories. Even communication would change. Signals moving through manipulated space-time would arrive sooner or later than expected, depending on how space is shaped along their path. Synchronization across distances would require new conventions. Clocks could no longer be assumed to agree simply because they were identical. Time itself would become something that must be managed. Long before people left Earth, the infrastructure of civilization would begin to feel the effects. Precision systems, navigation networks, and timing standards would all need revision. The practical consequences would ripple outward quietly, reshaping technology without announcing a revolution. Only after long periods of refinement would movement itself become conceivable. At that stage, the first uses of warp-like geometry would almost certainly be unmanned. Instruments, probes, and experimental platforms would test how objects behave inside manipulated space-time regions. Engineers would need to understand how matter interacts with space-time gradients, how radiation behaves near distorted boundaries, and how errors propagate when geometry is pushed too far. Failure modes would be unfamiliar. A conventional engine failure stops motion. A space-time control failure could alter where motion occurs. Misaligned geometry might trap objects, stretch regions unpredictably, or generate radiation through sudden curvature changes. Unlike mechanical systems, these failures would not be localized. They would be geometric. This is why early applications would likely be cautious and conservative. Warp-like effects might first be used to reduce travel time within the solar system rather than leap between stars. Distances could be compressed subtly rather than eliminated. The goal would not be speed, but reliability. Even modest gains would matter. Reducing months-long journeys to weeks would transform exploration and logistics. Compressing years into months would reshape mission planning entirely. Each incremental improvement would test assumptions about distance, risk, and coordination. As capabilities expanded, so would questions. Who controls access to space-time manipulation? How are routes regulated when space itself becomes navigable? How are boundaries defined when distance no longer guarantees separation? These are not engineering problems. They are governance problems, arising naturally whenever a new domain becomes accessible. History suggests that such questions rarely wait for technology to mature before demanding answers. There is also the question of reversibility. Space-time may be flexible, but it is not clear whether it always returns cleanly to its original state. Repeated manipulation could leave subtle residues, cumulative distortions too small to detect individually, but significant over time. The universe tolerates natural curvature, but deliberate, repeated shaping may push it into regimes evolution never tested. Physics offers no reassurance here. General relativity allows extreme geometries, but it does not guarantee their long-term stability when engineered repeatedly. Quantum effects may introduce noise, decoherence, or feedback loops that grow rather than fade. Warp-like systems might demand limits not because of ethics or politics, but because space-time itself resists sustained intervention. And then there is the question of visibility. Any deliberate manipulation of space-time is unlikely to remain hidden. Distortions propagate. Gravitational effects radiate outward. Even small adjustments, repeated often enough, could leave detectable signatures beyond their point of origin. At a certain level of capability, movement through space-time would no longer be a private act. It would announce itself to the universe in the only language space-time speaks: curvature. That realization reframes the entire pursuit. Warp-like travel is not merely a method of movement. It is a way of interacting with reality at its deepest structural level. Every use becomes an event the universe records. And long before humanity reaches the point of crossing between stars, it would be forced to confront a quieter realization. Learning to shape space-time does not just change how far we can go. It changes how visible we are. As the implications of space-time manipulation deepen, the central challenge becomes less about movement and more about restraint. Every new capability would expand the range of what is possible, but it would also narrow the margin for error. When geometry itself becomes a tool, mistakes do not merely damage hardware. They alter the environment in which everything else operates. This is where faster-than-light travel stops resembling transportation and starts resembling stewardship. Space-time is not an inert resource. It is the medium through which causality unfolds. Altering its structure, even locally, risks unintended consequences that may not appear immediately. A distortion created for travel could interact with surrounding curvature in subtle ways. Small asymmetries could grow. Feedback loops could form. Effects could propagate outward long after the original manipulation has ended. These risks are not hypothetical. General relativity allows extreme geometries, but it does not guarantee that all allowed geometries are stable when engineered repeatedly. Quantum effects further complicate the picture. Vacuum fluctuations, field interactions, and energy gradients could introduce noise into space-time control systems, turning precision into unpredictability. For this reason, any civilization approaching warp-like capability would likely move slowly, not because of hesitation, but because caution would become a survival trait. The temptation to scale up quickly would be strong. The cost of doing so prematurely could be catastrophic. Distance has always acted as a natural buffer. It slows conflict. It delays consequence. It forces commitment. Warp-like travel erodes that buffer. When separation no longer guarantees time to respond, decisions carry immediate weight. Cause and effect tighten. This changes how power functions. Control over space-time geometry would not simply enable exploration. It would redefine access. Routes could be opened or closed. Regions could become reachable or isolated. Influence would no longer depend on proximity alone. It would depend on geometry. History offers a consistent lesson here. Whenever a new domain becomes navigable, oceans, airspace, orbit, competition follows quickly behind discovery. Rules emerge only after friction exposes the cost of absence. Warp travel would not escape this pattern. It would amplify it. Yet there is another constraint, quieter but more profound. Space-time manipulation leaves records. Every curvature change produces effects that propagate outward. Gravitational disturbances do not vanish. They thin, stretch, and fade, but they persist. Over long periods, the universe becomes an archive of its own alterations. Natural events write into that archive constantly. Engineered events would do the same, but with structure rather than chaos. This means that a civilization capable of shaping space-time would not operate invisibly. Even if it chose silence, the geometry itself would speak. Repeated use would leave signatures distinguishable from natural processes, patterns that could be recognized by others who know how to listen. At that point, faster-than-light travel ceases to be a private achievement. It becomes a declaration, not of intent, but of presence. And that realization introduces a final layer of restraint. To move this way is not only to cross distance, it is to participate in the universe at a level where actions are preserved far beyond their immediate purpose. Before any civilization steps fully into that domain, it must confront a question that physics alone cannot answer. Not whether it can go farther, but whether it understands what it means to be seen. For now, faster-than-light travel remains unresolved. The equations allow it. The loopholes persist. The universe has not closed the path, but neither has it revealed a simple route forward. Each advance exposes deeper structure, tighter coupling between energy, geometry, and time, and a growing awareness that capability and responsibility are inseparable. This is not a failure of science. It is its normal state. Every profound shift in understanding begins this way, suspended between what is known and what is permitted. Flight existed in equations long before it existed in skies. Atomic energy lived in theory before it reshaped civilization. In each case, the universe did not change. Human understanding did. Warp-like travel now occupies that same space. It may turn out that deeper laws impose limits we have not yet encountered. That causality demands constraints subtler than speed alone. That space-time tolerates brief manipulation but resists sustained control. If so, the pursuit will still have mattered. It will have revealed something fundamental about the architecture of reality. But if the universe allows this path, even narrowly, then distance will cease to be the defining boundary of human experience. Stars will no longer be symbols alone. They will become places with consequences. Exploration will stop being speculative and start being experiential. The cosmos will shift from something observed to something engaged with directly. That transition will not happen all at once. It will unfold slowly, through measurement, refinement, restraint, and adaptation. Through mistakes that teach rather than destroy. Through patience rather than urgency. And through a growing understanding that faster-than-light travel is not about speed. It is about relationship. A relationship with space-time itself. With causality. With visibility. With consequence. The universe does not forbid us from asking these questions. It does not promise answers either. It simply responds to what we attempt, recording every disturbance, preserving every alteration, carrying each echo forward. Somewhere within that vast record may already lie evidence that others have asked these same questions before. Or it may remain silent, waiting. Either way, the pursuit has already changed us. Because once the possibility is recognized, once the question is asked seriously, the universe is no longer just a place we exist within. It becomes something we may one day shape, gently or disastrously, wisely or carelessly. The future of faster-than-light travel is not written in engines or equations alone. It is written in how patiently we learn, how carefully we proceed, and how clearly we understand that when distance finally yields, it will not be physics that decides what happens next. It will be us.